Okay, I'm going to start the recording. Cell phones away. The things that we are learning today is some new stuff. The first little box up there, it says the leading term of a polynomial can help you determine the end behavior. The end behavior. The end behavior is kind of like what we were talking about last class, when you can identify is something positive or negative, is something even or odd. So it's like looking at the two ends of the graph and how they relate to each other. So it says, look for two things. So that right here. Look for two things. So these are the two questions that will help you. And so if you're looking at a graph, you can determine the end behavior, but if you're looking at the equation, you can also determine end behavior. So the question you ask yourself is the leading coefficient positive or negative? And is the degree even or odd? So we're going to pretend like these are my leading terms, and we're going to identify those things. So this first one, is that leading coefficient, would it be positive or negative? It's positive. It's a positive 4. So we would say it's positive. And then what would the degree be, even or odd? Odd. Let's look at the next one. Negative x to the 6th power. Is that positive or negative? Negative, even or odd? Even. 3x to the 4th, positive or negative? And even or odd? Do the last one. Do you agree with me with the last one? Okay, so we said that whether or not your graph is positive, negative, is that the right arrow or the left arrow if you're looking at your graph? The right. Okay, so what we're going to do is we're going to give ourselves, we're going to draw a little picture with a right and a left arrow. So the first arrow that I can draw for each of them will be the right arrow. So if you're positive, you are facing up. If you are negative, you are facing down. And that is my right arrow. That is the right arrow. My word kind of blurred together, but I was writing right arrow above the positive and negative. So that's how I figure out my right arrow. And then to figure out my left arrow, so if I know that my right arrow is like this for the first one, my left arrow, this is an odd. So are they going to be the same or opposite? Odd is opposite. So if I have one pointing up, the other one has to point down. So I'm going to make my left arrow, and it will point down. And then if I'm even, I point same. So I'm going to go and put my left arrows down. Let's see if we get the same left arrows. Lenina, why do you have crazy eyes? Which one? So do you remember odd is opposite? Okay, so I have to start with my right arrow. So the one that I'm putting in second is going to be the left arrow. And so if I'm positive, I am pointing up. I have to start there. If I'm odd, the other one has to be opposite direction. If I'm even, they have to be in the same direction. Even, same direction. odd, they have to be in an opposite direction. So I'm making the left arrow right now. Any other questions on just being able to draw the arrows? The arrows can represent end behavior. And so today we're going to graph these. And as we graph them, it's kind of important to be able to identify end behavior just with the arrows. How are my two ends going to be? I'm going to be pointing up on the right and left on the down on the left one. Identifying those arrows is important. This is a fancy schmancy notation, but it is also just taking those arrows and writing it basically in a calculus notation. I have to expose you to it, so I'm exposing you to it. It is saying, so we've got left and right hand. They're going to be written in that order. So we're going to translate our up and down arrows to the math that we put here to answer the questions. The way that you read these, it says the limit as my x approaches, the arrow means approaches, negative infinity for my graph is, again, that sounds very mathy, but all it's asking is, which way is the left arrow pointing? Which way is the right arrow pointing? And so the way that we're going to describe these, if you're pointing up, you're going to positive infinity. If you're pointing down, you're going to negative infinity. So for the first one, my left hand is asking for the left arrow. The left arrow is pointing down. So we would call that what? Negative infinity. My right arrow is pointing up. We call that what? Positive infinity. So we're going to go through and we're going to fill in the rest of the blanks. I want you to fill them in. I'm going to fill them in. We're going to make sure that we both know how to fill in the blanks. If on the quiz or the test, you get stressed and you're like, oh, I don't remember how to answer these. If all that you can do is give me the arrows and you put arrows here, it's not going to give you full credit, but it's going to give you more credit than no credit. So if all you can do is the arrows, that is better than no credit at all. So the first step is just being able to identify those arrows. And then we just represent the arrows in math with positive or negative infinity. The last one? The first two? Okay, so are you good with how I represented the arrows? Okay, so anytime your arrow is pointing down, the left blank is going to be, sorry, it's not, I'm saying that wrong. Anytime you have a down arrow, it will be negative infinity. So I have a down arrow for both of them in the first spot. So in the first spot, they're both going to be a negative infinity. For the top one, I'm pointing up. Up is positive infinity. Down is negative infinity. That makes sense? Okay. So we're going to answer these questions. For question number 1, it says, use the leading term test. We just used the leading term test. We used the leading term to figure out which way the arrows go to answer the limit question. We're going to do the same thing. So for this one, is this one positive or negative? Negative, so I know I'm going to point down. And then is it even or odd? Odd, so they're going to be opposite, like that. So in my first limit blank, it's asking for the left arrow. The left arrow is pointing up, so I'm going to say infinity. the right arrow is pointing down. So I'm going to say negative infinity. See if you can answer the second question on your own. I'm going to answer it on the board. See if you can answer the second question on your own. What'd you mess up on, Adeline? Oh, over here? Oh, okay. So the very first term, it's a positive 1. So we have to have our right arrow is positive. Yeah. Yeah, that first term is powerful. The first term tells you a lot about a graph. Any questions on the limits, which are just end behavior? Let's flip over our paper and let's look at the very last question, which is number 5. Okay, looking at question number 5, it's asking us to do all these things, but part D says find the end behavior. Well, we just did finding the end behavior from an equation. Well, we could find it from a graph. You already have the arrows. You already know which direction they're pointing in. So I'm going to answer the limits for these, and I'm hoping that you can answer them too. Araya, how'd you do? Pretty easy, right? So with a graph, it's even easier because the arrows are already there. Gabriella, how are you doing? Pretty easy stuff? Okay. So the notation is kind of scary again, because it's the limit stuff, but I'm going to already give you the limit stuff. All you have to do is fill in the blank. So you're not going to have to write this out. I'm going to fill that out for you, and you just have to fill in the blank with either positive or negative infinity. Victor, you can. Oh, solutions. When we get there, I'm going to just remind you guys that when you find zeros, zeros are the same thing as solutions. Danny, would you open the door for Will, please? Well, she left her flowers in here. I moved them because I was hoping she wouldn't come back for them, but I put them safe. Moving on, a polynomial function f of x is equal to x with n degree, which is bigger than 1, greater than or equal to 1, has at most whatever that exponent is. So the degree, we talked about this last time, that the degree determines the possible real zeros. So it's equal to whatever that exponent is. And if you have that many real zeros, the amount of turns, so we also talked about how these graphs have a lot of wiggles in them. So every wiggle or every time you change direction, that's called a turning point. Your turning points are just 1 less than that. So it's n minus 1. So your turning points are just 1 less than that. So what I want us to do is go down here. We're going to skip this for a minute. We'll come back to it. For these 2 questions, it says determine the following, and I give it to you, these functions. I give them in standard and in factored form. So this is standard form. This is factored form. So I give them to you in both forms. Part A says determine the possible real zeros and the number of turning points. So we talked about last class that the number of possible real zeros, it's at most equal to the degree. So what is the degree of the first function? 3. That means that I can turn one less than that. So the turning points, how many is that? 2, one less than that. Okay, let's look at the second one. The second question, what's the degree of the second one? 7. So how many turning points? 6. Okay, what that means, to give you an example for the first one, if it has 3 zeros, so if I've got a function and it crosses the x-axis 3 times, is this one positive or negative? Positive, you look at the very first term, it's positive. So I would start up and I just wiggle through. It has a degree of 3. So I know that my function would be odd. So I'm pointing in opposite directions. So if I have 3 zeros, the amount of turning points that I can have if I'm going through my graph, here I change direction. So that's 1. And then I go down, up, I change direction, I'm going up again. So however many times you cross the x-axis, you can have 1 less than that wiggles. And that's the reason why. So, yes, sir. It's 1 less than the first one. So if you have whatever the degree is, it's 1 less than that is how many turns you can have. So if we thought about something really simple, like a line, y equals mx plus b. Well, it doesn't really matter what the slope or the y-intercept is. The x is to the first power, right, for a line? So something really simple like y is equal to x. That's just parent function line. If you are to the first power, what is your degree? 1. And so how many turning points can you have? What's 1 less than 1? Okay, well, if you have a line, how many times does it change direction? None. That's what it means. How many times can your graph change direction? Lines don't change direction. They keep going in the same direction. Okay, so even in odd multiplicity, another way to think about this is repeated roots or repeated roots or repeated solutions. Repeated roots or repeated solutions. So for these, every single factor has a multiplicity. It's either listed once or it's listed multiple times. So what I mean by that is if we look down here at our 2 examples, this first factor, it's to the first power. We don't have to write the 1, but it is to the first power. The second factor, do you see how it's written the second power? So it repeats. The factor happens more than once, it happens twice. So anytime that you have an even factor or an even multiplicity, so this one is an even, this one's technically an odd because it's the first power. Over here, that one would be an odd multiplicity. This one also would be an odd because they're first power. This one's the second power, so this one is also an even multiplicity. When you go to graph them, which is our goal here, when you go to graph them, even multiplicities, they will bounce. They will bounce. And you can simplify both of these things down to something to the first power, something to the second power. So I already put something up to the first power. Something to the first power is odd, because that's like to the first power. Something to the first power is odd, and it will go through. Odd will go through. And it will go through like a line. It behaves like a line. Even functions, they bounce. They bounce. This would be like y is equal to x squared. They bounce like a quadratic. Okay. Even functions bounce like a quadratic. That's to the second power. They bounce at every root. Odd functions go through. So wherever your root is or your solution, an odd function will go through it. So even functions bounce. Not even functions, even multiplicities go bounce, odd multiplicities go through. Most of the time, your functions go through. But we always check for even multiplicities. So this is the same thing that, like, if it's odd, it could be to the first, third, fifth, seventh, anything that is an odd exponent. Anything that is an even exponent, if it's squared or to the fourth power, it's even. So what we're going to do is we're not going to look at standard form anymore. We're going to look at the factored form. So factored form, you can figure out the solutions. That's when we set every single factor equal to 0 and solve them. So every factor set equal to 0 and solve. And these are not going to take you any time because they're very simple. So if I set this equal to 0, x minus 4, what does x equal? 4. So that's one of them. And that factor is to the first power. Okay, so it's not repeating. So you only have to notate it here if it repeats. The second one, x plus 2, what is x equal to? -2. And it repeats, right? Okay, so we could call that a multiplicity of 2 because it happens twice. Hello? I do not. It didn't show up, but I mean, half my class is out for 8th grade invasion, I feel like. Are we not supposed to mark them absent if they are? I thought we weren't supposed to mark, I thought we were supposed to mark them absent if they're not here because whatever club they go to would be saying whether or not they showed up, right? Like just absent, yeah. No. Bye. And there are no more factors, so we're done with factors. So when you find there are no more factors, so we're done with solutions. Solutions are just another way for the roots or the zeros, all the same thing. So this says that we should have 3 zeros because it's to the third power. And we actually do because here's one of them. And then this one is twice. So that's 1, 2, 3. For part B of the second equation, which again, these are the same thing, we're going to go through and we're going to look at each one. So this is a tricky one. So it's basically saying if I took that and I set it equal to 0, well, what's x equals 0? It's just 0. So anytime you have an x and it's out in front, it is just 0. So x is equal to 0. And how many times that's repeating? 3. So we would say multiplicity of 3. The next one, for x plus 1, what is x equal to? -1, and it's to the first power, so it doesn't repeat. X minus 1, equals, is x is equal to 1, and it doesn't repeat. And x plus 5 means x is equal to -5 with a multiplicity of what? Are we good so far?
So I can get the numbers from 8.
How did I get these numbers? A? Oh, the top, the possible real zeros. You look at the degree. So this is a third degree. So you could have 3 possible zeros. 1 less than that means I could have 2 turning points. Here, it's a 7th degree, so I could have 7 possible real zeros. And 1 less than that says that I could have 6 turning points. So you could list it as like third, for A, this is the degree. And this is the turns.
And for the bottom,
Mhm.
you just do an equal 0.
And then I only have to make a note of it if it has an exponent other than 1. So when it has an exponent of 1, you just write it. And then only if it has an exponent of something other than 1, you're going to write down how many times. So it's like, how many times is it happening? And that we call that a multiplicity.
I don't 3.5 times. So multiply by 8.
Like here, the
Yeah.
parentheses. Yeah. Yeah, I was trying to figure out what you meant. Hashtag. Yes, the ones I put in parentheses. Yes. We good so far? Okay, let's take a little break. Oh, over here. We're gonna do emoji Pictionary again. We're gonna see how good you guys are at Disney movies. Well, let's see. Well, Pixar is not Disney. Oh, well, I guess it is. Disney Pixar? Yeah, I guess it is. Okay, Disney movies. Aladdin. Frozen.
Princess and the Frog.
Y'all are good.
Cinderella.
Mhm. Up.
Yeah.
Oh, yeah, really. No, wait. This not what?
What does this say?
Well, look at that. Oh,
Nope. Nope.
Mulan.
Mulan.
Toy Story?
Toy Story. Dumbo.
Never actually watched.
I was little when I saw it.
Oh, Snow White.
Snow White and the Seven Dwarfs. Mm-hmm. Lion King. This one's Beauty and the Beast. Yeah. Close. Finding Dory. Dory. Mm-hmm. Yep. Y'all are good. Y'all are good. Okay, so we're gonna flip over to the back and we are going to start graphing some of these. So we are gonna do some really big kid math. So it says determine the following, and then we're gonna graph. I give this to you in 2 different forms. I give it to you in standard form and I give it to you in factored form. Part A says apply the leading term test to determine the end behavior. So what we can write down right here, I didn't put the limit stuff here. I just want us to write down the arrows. Which way should the arrows be drawn? So for this one, let's look at how those arrows are going to draw. It says negative function. So my right arrow is going to be down, and then it's even. So they're the same. So both arrows are going to point down. That will help us. Part B is finding the solutions. So the solutions are when we take each factor and we set it equal to 0. As we do so, we're going to note any of the multiplicities. So the first one, if I set negative x equal to 0, it's just 0. So x is equal to 0. If I have x is equal to negative 1, or sorry, yes, x is equal to 1. And it's a multiplicity of 2. And then I have x is equal to what? Negative 2. Good job. What I like to do anytime I have an even multiplicity, I like to go through and I circle that value. I circle it because I bounce there. So when I go to make my graph, I'm going to bounce there. So I want to remember that I bounce. So what I'm going to do now is I'm going to take and I am going to mark my graph, and all I care about is marking the x-axis. These are x equals, so I'm going to go mark the x-axis. So as I mark the x-axis, I'm going to mark anything with a circle around it. I will mark it with a dot. And you don't have to do this. You can mark it with everything with a dot. But my one, it has a multiplicity of 2. So I'm going to mark it with a dot. The other 2, I'm going to mark with a little x. And I mark them with a little x because the x I think of as like a door. So a door, you can go through a door. So we will go through at those points, but I bounce anywhere I see the dot because it's like a ball. I bounce there. So I know that we're ready to graph now. That's all I needed to know. I am ready to graph. When we make our arrows, which one do I make first? The right one, always. So because I make my right arrow first, I have to start with my right side, and I'm going to make my right arrow. And so I just connect my right arrow back to my very first point. From there, and this seems weird, but I'm going to sketch my graph backwards. So I'm going to take it and I'm going to wiggle through backwards unless I bounce. So most of the time I go through, but for some of them, so like at 1, I bounce. So I need to erase that. I went too far. I was too. Okay. So I'm going to have to be careful because I have to come back through. As I go through and I weave, I'm going to have to come down because it bounces, but I have to go back up because I have to go through right here. It's an x-intercept. And then I'm going to I go through. So I go up, but then I'm going to have to turn because I have to go back through. And since I go through, I will end back down. So another thing you can do is draw both sides, but you have to make one match the other. And to always make it work, you have to start on the right side. So I know that this one bounces. And then these 2 go through. So my graph ends up looking something like that. If your little humps are bigger, like if you drew yours up higher or you drew it down lower, I don't care. What I do care about is that if you bounce or go through, and if the ends of your graph are pointing in the correct direction. That is what I check for when I grade any of the graphs that you do on your own. I'm checking for that. I don't care how big you make your little bumps. I don't care. So as you check, you need to make sure your arrows are pointing in the right direction. I'm good. Did I bounce there? I did. So do you guys see what it means to bounce versus go through? Okay, you bounce off and go in the same direction. And so another way to think about it, even functions, they end in the same direction. So around an even multiplicity, you leave it and go in the same direction. around something with an odd multiplicity or anything to the first power, you leave that root and you go in opposite directions. All right, well, we did a graph. We're done with it. The next one. Let's see how far you can get on your own. And if you get stuck after A, you can look up and get unstuck. And then try B on your own. And if you get stuck, look up and check B. So I want you to try and see how far you can get on your own. And if you have to look up, that's okay. Not just any multiplicity. If it was a multiplicity of 5, it still goes through. So anytime it's an odd, it goes through, or they leave that root in opposite directions. If it's an even, it's only if it's even that you hit a root and you have to go in the same direction, whether it's up or it's down. You have to go in the same direction from the root. So only even multiplicities. So the second one, you see how that is to the first power, to the first power, to the first power. Those are all odd. So you don't bounce at all on the second one. You go through everything. More often than not, you just go through. Trying to figure out what? Most of the time you do. It's only special cases that you bounce. So I got to this part where I just went and marked my graph. If you want to mark them all with a dot, that's fine. However you want to mark your graph. I just try to remember, and sometimes I forget, but I try to remember to mark mine with X's, saying that it's like a door. I can go through there. And then I'm going to mark my ends. So I know that on the left, when I leave that root, I go down, and on the right, when I leave that root, I go up. From here, you go through at every point. So this one, it doesn't really matter if you move from left to right or right to left. It's not going to change anything. So you just connect the dots from there, and you just weave through. Again, if your wiggles are a little higher or a little lower than mine, I don't really care as long as I can see that they are curves and not points. They're not like mountains, they're like hills. How are we doing so far with graphing? It's pretty easy. Graphing polynomials is easy. Once you mark your graph, you just weave through. The next section, gives us 2 descriptions. It says, write a polynomial of minimal degree. That means that, like, if you had an option and it was supposed to be like an odd multiplicity, you wouldn't want to put it to the 5th power because that's just making it more complicated. So we have minimal degree, which these we don't even have any freedom because it tells us. With the following roots, remember a root is just a solution. So all we're going to do is write a function. So if it's a function, they both have to start with f of x. And for these, all we're doing is working backwards. If I tell you that x is equal to 0 in the problem, what does it look like? Let's go find one. Here, it says x is equal to 0. What did it look like up here? It is a negative, but did it have to be negative? No, here x is 0 and it's just x. So I'm not going to put the negative unless there's some indication to tell me it's negative. So anytime you see x is equal to 0, the way it will look in your problem is just an x out front. So I'm going to put an x out front. And then it looks like I've got 2 factors. After that, they're both going to have an x. The first one, if x is equal to 4, what do I put in the parentheses? Minus 4. And then it says multiplicity of 2. So what do I do now? Square it. I put it squared. Multiplicity of 2. And so for my last factor, x is equal to negative 2. So what do I put in parentheses? Plus 2. That is it. We're just writing it going the other direction. I want you to see if you can write the second one. See if you can write it with the given solutions. So it looks like I'm going to have 3 factors. None of them are 0. So there's going to be no x out front. So I can even start with, I've got 3 factors. They all have an x. And I just plug in what I get. Did y'all get the same thing? If you have a question on your quiz, let's get this question right. That one's easy. It's like nothing involved. Grace, how'd you do? What part did you mess up on? Oh, you put this one? Oh, so you put it too soon. Any questions on these? I think you have like 4 questions on your homework that's like this, so get those right. We only have one last thing to do, and it's analyzing a graph. So from the graph, can we figure out these things? Well, we already found the end behavior. We already did that. So part A, it says determine if the leading term is positive or negative, and if it would be even or odd. So for the first one, is it positive or negative? Negative, because it points down. They are pointing in the same direction. So is that even or odd? Even. Part B, it says locate the zeros and just determine the multiplicity. If it goes through, you don't have to really think about it. It just is that one. So if I'm looking at my zeros, I see 3 of them. At -2, I go through. At 0, I go through. But at 1, does everybody agree and see that you bounce at 1? So I'm going to give myself a little note that I bounce. So to locate the zeros, these are just the solutions. So Victor, you had asked why did I write that to the side? Because I want you to know that we're actually if you are solving a polynomial, that's what we're doing. We're finding the solutions. So the solutions, and I'm just going to list them. They can be in any order that you want. You just need to make sure you have them all there. And I'm going to use the lowest multiplicity possible. I know it bounces. So technically, it could be to the 4th power or with a 6th multiplicity. Any even multiplicity would cause that to bounce. I'm going to pick the lowest one, which is a multiplicity of 2. Part C says we're going to write an equation. Well, if I know the x's, I can write an equation. This is just like what we just did. So I have to start with f of x. And I see that x is equal to 0. Anytime x is equal to 0, I just throw an x out into the front. And then I'll list my other 2. And I just change the signs. I have to make sure that the x minus 1 term is squared, though. Y'all feel okay about this? Let's do the second one on our own. If you get stuck, then you can ask. Oh, I want to pause for a minute. So remember on the first one that we said it was even? You can always double check and look at your X's and see if you have an even amount of them. And so if I look at my answer, it should be an even amount of factors. So I have 1, 2, 3, 4. 4 is an even amount. So they have to match. They have to match. So if they don't match, there's probably some multiplicity that you missed. Ooh, the second one's easy because they're all an odd multiplicity. Come on, how'd you do? Yeah, it's pretty easy. A little bit. Vincent, how'd you do? All right, that is it. So we have a good amount of time actually because I'm with y'all longer today.